Welcome to this video on electronegativity. In this video we're going to look at electronegativity and then relate this to the different types of bonds that we're familiar with. First we want to get started with what exactly electronegativity really is. And the easiest way of describing electronegativity is it's an atom's pull or attraction for the electrons in a chemical bond. How badly does that atom want those electrons? And we're going to put a lot of things when we're talking about bonding in terms of a struggle for those electrons in a bond, kind of a battle for what's happening with those electrons in that bond. If you look at a periodic table, there's a periodic trend that deals with electronegativity. And electronegativity is going to increase as you move to the right on the periodic table and as you move up. And there's kind of an easy way of remembering this when you're looking at the periodic table. I like to think of it as fluorine is going to be the most electronegative element. If you can kind of remember that and you think about fluorine's position on the periodic table, you're always going to get this trend correctly, that as you're moving to the right and as you're moving up, electronegativity is going to increase because fluorine is that most electronegative element and it's in the top right. So it makes sense that it would be increasing as we move up and increase as we move to the right. Now, you may be looking at the periodic table right now and saying, hey, there are some elements to the right of fluorine. Why wouldn't those be the most electronegative? Well, if you look to the right of fluorine, you're going to find neon. When we think about neon and some of these other noble gases, they don't normally form bonds with other elements. And if electronegativity talks about the pull an atom has for the electrons in a bond, if you're not bonding with other elements, you're not going to have an electronegativity value. So we're not really having any electronegativity values for those. With this basic idea of what electronegativity is, we're going to relook at some of the bonding principles we've talked about earlier this semester, but now relating them through electronegativity, and we can kind of get a little bit more details as to what's happening with the bonding. And we're going to look at three different scenarios. The first scenario we want to look at, the first case, is when two elements have a very large difference in electronegativity. That means one's going to be very electronegative and the other one is not going to be very electronegative. You're most likely to see this whenever you have a metal bonded to a nonmetal. Now right away, we recognize that when you have a metal bonded to a nonmetal, you're looking at an ionic bond. We've seen that before. And if we use kind of our most common ionic compound to represent that, when we're looking at something like NaCl, right away, even before we think about electronegativity, we recognize that as an ionic compound. We're really going to think about that as sodium ions and chloride ions. There's not going to be any sharing of the electrons here. These two elements are incapable of sharing electrons. They just can't share. And one of the reasons that they can't share is chlorine is very electronegative. Being chlorine is very electronegative, it really wants the electrons. It wants the electrons and it wants them bad. It's almost as electronegative as fluorine. So chlorine, really electronegative. Sodium, complete opposite side of the periodic table, a metal, not electronegative at all. Sodium is not very electronegative and doesn't want the electrons. So in this struggle, this battle for the electrons, chlorine really wants it, sodium, not really so much. And because of that, chlorine's just going to be able to rip those electrons away from sodium, and sodium is not electronegative enough to put up a fight. That means we can't share electrons. If we can't share electrons, we're going to get an ionic compound. So that's what we're looking at when you have a big difference in electronegativity, just like we would see with metals and nonmetals. The next case is when there's no difference in electronegativity values. You're most likely to see this when you have two nonmetals with the exact same electronegativity values. And for us, what that generally is going to mean is usually two of the same element. That's the easiest case to kind of look at. Now, right away, we know that when we have two nonmetals, we're definitely looking at a covalent bond. We've seen that many times before, as that's what we're looking at when we have two nonmetals. There's going to be a sharing of the electrons there. For this example, to keep it as kind of straightforward as possible, I want to use chlorine gas. Chlorine gas is Cl2. So that would be two chlorine atoms bonded together. So when we look at chlorine bonded to chlorine, each chlorine atom is going to have the same electronegativity as the other chlorine atom. There's going to be an equal pull for those electrons in this bond. If there's an equal pull for the electrons in that bond, no one's going to win. It's kind of like a tug-of-war game. In a tug-of-war game where you have equal strength opponents and they're each pulling on the rope equally and oppositely, no one's going to win that. So that's going to result in the electrons being shared. Not only are they going to be shared, but because of the exact equal strength of electronegativity, they're going to be shared equally. We're going to go into a little bit more details with bonding. Already you would recognize this as a covalent bond, sharing of the electrons. But we need to introduce some other terms for this to kind of be a little bit more specific. We call this type non-polar covalent bond. And we can compare and contrast this to what we're going to do next, where we have a polar bond, but non-polar means everything's going to be the same. There's not going to be two distinct regions in this molecule. So the first two cases kind of dealt with the two extremes. Case one dealt with ionic compounds, where we had a big difference in electronegativity. Kind of the other bookend, case two, when you had exactly the same electronegativity values. There was no difference. Well, there's a lot of middle ground between those. And the middle ground is when you get two elements with a small difference in electronegativity. You're going to come across this scenario when you end up with two different nonmetals trying to bond together. A good example of that, if we kind of keep chlorine as our common element when we discuss how chlorine is going to bond, would be something like BrCl. You recognize both bromine and chlorine as nonmetals, so this must be a covalent bond, but this is going to be a special type of covalent bond. So I kind of want to compare and contrast this to the two other cases that we had. First case, ionic. This is not going to be an ionic compound. Bromine and chlorine are going to share electrons. Chlorine's only slightly more electronegative than bromine. So it has a little bit more of a pull on the electrons, but not a whole lot. We're not going to be in the scenario that we were earlier with NaCl, where chlorine could just yank the electrons away from sodium. That's not what we have here. Instead, bromine's able to put up a fight. It's close enough to chlorine's electronegativity value of its own that it's going to put up a fight. It's going to be able to hold on to those electrons. Chlorine just can't outright steal those electrons. So we're not going to be in that scenario. We're not going to be in the scenario that we saw with Cl2 either. Because in Cl2, that case 2 that we just saw, both of the chlorines had the same electronegativity, so the electrons were going to be equally shared. Here, chlorine is slightly more electronegative than bromine, so we can still share the electrons, but these electrons aren't able to be shared equally. We're going to be looking at some form of unequal sharing. We call this type of unequal sharing that we're dealing with a polar covalent bond. This is this unequal sharing of the electrons. So let's kind of look at what this means for BrCl Now I kind of want to give you a non-chemical way of kind of looking at this. So when we look at BRCl, there are going to be shared electrons in here. But the electrons are not going to be equally shared. Chlorine's slightly more electronegative than bromine, so it has a little bit stronger pull on those electrons. Well, if you think about what electrons are negatively charged. So what this means is the electrons are going to spend slightly more time closer to the chlorine than they will the bromine. If the chlorines are going to spend slightly more, or if the electrons are going to spend slightly more time closer to the chlorine, you're going to get a partial charge buildup. And the way we designate a partial charge buildup is we sometimes call that a delta minus, or a partial negative. That's the lowercase Greek letter delta. And when you see that, that's going to be partial. So that's going to be a partial negative charge. That doesn't mean it's a full ion. That just means I have a little bit of negative charge buildup. If the electrons are spending a little bit more time closer to the chlorine, they're going to be spending less time closer to the bromine. So if they're spending less time closer to the bromine and electrons are negatively charged, I'm going to get a partial positive charge buildup on the bromine. Bromine will have the partial positive, chlorine will have the partial negative charge. So you can see we have two distinct regions of the molecule, two distinct poles. That's why we end up calling this a polar covalent compound. There's two distinct regions, kind of like two different poles on a magnet, or the two different poles on a battery. There's two distinct regions. It's not uniform anymore. That's that polar covalent bond. So besides denoting this with the delta plus and the delta minus, there's also something called a dipole moment. I want to show you what that means for this type of molecule. And for a dipole moment, what you do is you draw an arrow towards a more electronegative element. So here's the dipole moment for BRCl. It's directed, pointed at that more electronegative element. That's kind of showing where the electrons are being pulled to. Now, what we also do, kind of as a little bit of symbolism, the electrons are being pulled towards the chlorine. We often, on our arrow, make a little hatch. That little hatch, if you look at it closely, it kind of looks a little bit like a positive sign. That's a subtle reminder that the other side of the molecule is going to be slightly positive. So that's what you see when you see a dipole moment. The dipole moment points towards that more electronegative element. In this case, that's going to be the chlorine. So this idea of unequal sharing of electrons, a little bit not familiar with. So I'm going to put this in a non-chemical way. And kind of the non-chemical way I have of kind of explaining this to you is something that I think will be pretty clear if you have a sibling. Even if you're an only child and don't have a sibling, you probably know people of siblings that have siblings. You can probably still imagine what happens here. So if you have a sibling, I want you to think back to when you were both when you were both children. Your parents probably told you to share a toy or share something. Now, what did they actually mean? Well, what they actually meant was kind of like case 2, equal sharing of the electrons. Well, those of you with siblings kind of know this to be true. It probably never actually went down that way of perfectly equal sharing, right? Somebody got the toy or the item more often than somebody else. Whoever was bigger, older, meaner, stronger, more clever, more determined, ended up getting that toy or that item more often. But chances are it didn't end up with, like we see in case 1, where that person always got the toy or that item. Well, because then you'd end up getting in trouble with mom or dad. Most likely it probably rolled out just like what we're looking at here in case 3. The item was shared, but it wasn't equally shared. One of the siblings spent a little bit more time with the toy than the other one. Maybe it was 35 minutes with the toy, the other one only got 25 minutes. You know, more nights in one person's room than the other person's room. That's that idea of that unequal sharing. And that's what we're seeing here for when you have two different nonmetals. These electrons are being shared, but sharing doesn't have to happen perfectly equally. There can be an unequal sharing in terms of thinking about what's going to happen. And if there's unequal sharing, there's going to be that partial positive buildup and that partial negative buildup that you're seeing with that.